eVTOL flying cars. Imagine being stuck in traffic during rush hour. Cars barely moving. Time slipping away. Now imagine pressing a button, and instead of waiting, your vehicle lifts straight into the air and flies over everything. That's exactly what eVTOL flying cars are designed to do. eVTOL stands for electric vertical takeoff and landing. And unlike traditional aircraft, these vehicles don't need a runway. They rise vertically using multiple electric rotors. Similar to drones, but scaled up for human transport. This single feature completely changes how transportation could work in crowded cities. But the real story isn't just about flying, it's about solving a problem. Urban congestion. Cities across the United States lose billions of hours every year to traffic delays. eVTOL systems are being designed as a solution, allowing short, direct flights between rooftops, small landing pads, or designated hubs. Technologically, these vehicles are incredibly advanced. They rely on distributed electric propulsion, meaning multiple independent motors provide both lift and stability. If one fails, others can compensate. Add to that AI-assisted flight control systems, and suddenly flying becomes less about piloting skill and more about system management. However, one major limitation still stands in the way: battery technology. Current batteries limit how far these vehicles can travel and how often they can operate efficiently. Charging infrastructure is also still under development, especially for urban air mobility networks. Despite this, major companies are already running real-world tests across the US, and early results are promising. And once vertical flight becomes reliable, the next question naturally follows. What if that same vehicle could also drive on the road? Roadable aircraft. Picture this scenario. You leave your house in the morning, drive like any normal car through city streets, reach the edge of town, and instead of staying on the highway, your vehicle unfolds its wings and takes off into the sky. That's the idea behind roadable aircraft. Unlike pure flying cars, these vehicles are designed to function in two completely different environments: roads and airspace. They typically feature foldable wings or detachable flight systems that allow them to transition between driving mode and flight mode. The biggest advantage here is flexibility. You're not dependent on airports. You don't need to book flights or deal with delays. You simply drive, then fly when needed. For long-distance personal travel, especially in areas with limited airport access, this could be a game changer. Modern designs have come a long way from earlier prototypes. Lightweight composite materials reduce weight, while improved aerodynamics increase efficiency during flight. In driving mode, they behave like regular vehicles. In the air, they operate more like small airplanes. But this dual functionality creates a serious challenge: regulation. These vehicles must meet both automotive safety standards and aviation certification requirements. Two completely different systems, with strict rules. That makes development slower and more expensive. There's also the issue of infrastructure. Even if they can drive on roads, they still need space to take off and land. Still, the concept continues to evolve because it solves a key limitation of pure flying vehicles: dependence on dedicated air systems. And that leads engineers to ask an important question. What if you could achieve both vertical takeoff and efficient forward flight without needing traditional wings at all? Tilt-rotor flying cars. Tilt-rotor flying cars take one of the most advanced approaches to personal air mobility. And it all comes down to how they generate movement. Instead of relying on fixed wings or permanently vertical rotors, these vehicles use engines mounted on rotating structures. During takeoff, the rotors face upward, generating vertical lift like a helicopter. But once the vehicle is airborne, those same rotors tilt forward, transforming the aircraft into something that behaves more like a plane. That transition is the defining feature, and also the biggest challenge. Because shifting from vertical to horizontal flight isn't just a mechanical movement. It requires perfect synchronization, balance, and control. Even a small error during this transition phase can create instability, which is why engineers invest heavily in precision systems and automated stabilization. But when it works, the result is incredibly powerful. Tilt rotor systems combine the best of both worlds: the ability to take off vertically without a runway, and the efficiency of forward flight at higher speeds. This makes them ideal for medium-range travel where both flexibility and performance matter. However, this complexity comes at a cost. These vehicles are mechanically demanding, expensive to maintain, and require advanced safety systems to ensure reliability. There's also a concern about exposed rotors, especially in dense urban environments where safety risks must be minimized. And that raises an important design question. Can you achieve similar performance while making the system safer and more enclosed? That question led to the development of a different propulsion approach altogether: duct fan flying vehicles. Duct fan flying vehicles approach the idea of flight from a safety-first perspective. Instead of using open, exposed rotors, these systems enclose their fans within protective circular structures, often referred to as ducts. At first glance, this might seem like a small design change, but it has a major impact on how these vehicles operate. The most obvious advantage is safety. By enclosing the spinning blades, the risk of accidental contact is significantly reduced, which is especially important in urban environments where vehicles operate close to buildings and people. But that's not the only benefit. Duct fans also help control airflow more precisely, which can improve stability during flight. They tend to produce less noise compared to open rotors, making them more suitable for city use where noise pollution is a serious concern. However, this design introduces its own set of challenges. Airflow within a duct can create resistance, which may reduce overall efficiency if not engineered correctly. That means designers must carefully balance performance with safety, often using advanced aerodynamic modeling to optimize airflow behavior. Despite these challenges, duct fan systems are becoming strong candidates for urban air mobility solutions, particularly in air taxi applications where predictability and safety matter more than extreme speed. And once you start thinking about air taxis, a bigger idea comes into focus. What if these vehicles didn't need a pilot at all? Autonomous air taxis. Now imagine this. You open your phone, request a ride, and within minutes, a flying vehicle arrives to pick you up. No driver, no pilot, no human control. That's the vision behind autonomous air taxis. These systems are designed to operate entirely on advanced software and sensor networks. They use artificial intelligence, real-time environmental scanning, radar systems, and satellite navigation to move safely through complex airspace. Unlike traditional aircraft, autonomous air taxis are not built for long-distance travel. Their focus is short, efficient trips within cities, connecting rooftops, transportation hubs, and designated landing zones. From a technology standpoint, the progress is impressive. Redundant systems ensure that if one component fails, others immediately take over. Flight paths are optimized in real time, and collision avoidance systems constantly monitor the surroundings. But the biggest challenge isn't engineering. It's human psychology. Will people trust a machine to fly them through the air without a pilot? Public acceptance will play a huge role in determining how quickly these systems become mainstream. Even with proven safety, Trust takes time to build. However, if that trust is established, autonomous air taxis could transform transportation the same way. Ride-sharing platforms changed urban mobility. And once driving and flying become automated, the line between them begins to disappear completely. Hybrid car helicopters. Now imagine a vehicle that doesn't just switch between driving and flying, but actually transforms. Hybrid car helicopters are one of the most visually striking concepts in the entire flying car space. On the ground, they look and behave like standard cars, compact, road legal, and easy to maneuver. But when it's time to leave the road, something remarkable happens. Rotors deploy. The vehicle shifts its entire function, lifting off like a helicopter and entering controlled vertical flight. This transformation is what makes the concept so fascinating, but also what makes it incredibly difficult to engineer. Combining two completely different transportation systems into one structure creates serious challenges. Weight becomes a critical issue, because every added component reduces efficiency. Fuel or battery consumption must be balanced across both driving and flying modes, and mechanical reliability has to be nearly flawless, since failure in either system could have major consequences. Yet despite these challenges, engineers continue to explore this design. Why? Because it represents true independence. Unlike vehicles that rely on dedicated infrastructure like runways or specialized hubs, hybrid car helicopters aim to give users complete control over how and where they travel. You're not switching between systems. You're carrying both with you at all times. Advancements in lightweight materials and electric propulsion are slowly making these designs more realistic. What once seemed impossible is now entering early prototype stages. But as engineers refine these systems, a new idea begins to take shape. What if you could simplify the design and focus purely on efficiency once airborne? Fixed-wing folding cars. While many flying car concepts focus on vertical takeoff and flexibility, fixed-wing folding cars take a different approach. They prioritize efficiency. At their core, these vehicles function like small airplanes with an added twist. Their wings can fold in and out. When driving on roads, the wings remain compact, allowing the vehicle to maintain a standard car-like shape. But when it's time to fly, the wings extend, transforming the vehicle into an efficient fixed-wing aircraft. This design offers a major advantage once in the air: energy efficiency. Unlike rotor-based systems that constantly fight gravity to stay aloft, fixed wings generate lift naturally as the vehicle moves forward. This results in smoother flight, longer range, and lower energy consumption, making them ideal for longer trips. But there's a trade-off: takeoff requirements. Most fixed-wing systems still need a runway or some form of assisted launch. That means they don't offer the same level of flexibility as vertical takeoff vehicles like eVTOLs or helicopters. Even so, they fill an important role. They act as a bridge between traditional aviation and personal transport, combining the familiarity of airplanes with the convenience of road travel. For users who prioritize distance and efficiency over vertical convenience, this could be one of the most practical designs. But not every future concept is focused on flying higher or farther. Some are asking a completely different question. What if we didn't need full flight at all? Personal hover concepts. Not every vision of the future involves vehicles flying thousands of feet in the air. Some of the most experimental ideas focus on something much simpler: hovering just above the ground. Personal hover concepts aim to eliminate one of the biggest limitations of traditional transportation: friction. Instead of rolling on roads, These vehicles lift slightly above the surface, allowing them to move freely without direct contact. This could reduce wear, improve efficiency, and potentially eliminate traffic constraints in certain environments. There are several approaches being explored. Some designs use air cushion systems, similar to hovercraft, where a layer of pressurized air supports the vehicle. Others experiment with microthrusters that generate controlled lift. More advanced concepts even explore magnetic or electromagnetic systems, though these are still largely theoretical. The advantage of hovering is that it avoids the complexity of full airspace navigation. These vehicles don't need to integrate into crowded skies or rely on complex flight regulations. Instead, they operate at low altitudes, within controlled environments. But there are challenges. Stability, energy consumption, and safety in unpredictable conditions all remain significant obstacles. Even small variations in terrain or weather can affect performance. For now, most hover concepts remain in early development stages. But they represent something important. Innovation doesn't always mean going higher. Sometimes, it means rethinking the problem entirely.